So we're going to hit up our first example of calculating delta S for a reaction. Now these calculations work just like delta H calculations. You look up the values in the table and you write them out for each one. You take into account the stoichiometry and the equation and so forth. So we're going to look at 2 C4H10s as a gas plus 13 O2s as a gas makes 8 CO2s as a gas plus 10 H2Os as a gas. That was one of the equations that we calculated delta H for in our previous kind of our warm-up of the chapter. Okay? So now I'm going to take the same reaction, I'm going to go to the table in the back of the book. That same table, the delta H table in the back of the book, has one column for enthalpy changes, another column for entropy changes. Now we're going into the delta S column of that table. So we're going to look up delta S for a reaction in joules per mole Kelvin. So I'll put that on the other end over here so we can see it better on the camera. Units are joules per mole Kelvin. Temperature has to play into it because temperature affects entropy. As you warm something up, temperature changes. So the units are different in two ways from delta H. Delta H's were calculated in kilojoules per mole. This is joules per mole, and there's a Kelvin in the denominator. That's an important thing to keep in mind as you work your problems. So we go to the table, we look up each substance in the phase that it's in. So the enthalpy of, the entropy of formation for each of these substances, delta S is plus 310.2 for C4H10, plus 205.0 for O2. This is not zero because the formation of O2, two atoms of O forming an O2, that's going to be a change in entropy. Plus 213.6 for CO2 and plus 188.7 for H2O, joules per mole Kelvin. Change in entropy for the reaction, delta S 0 for the reaction. We're going to calculate it just like delta H, folks. It's the sum of the delta S of reaction, delta S for the products minus the sum of delta S for the reactants. Still products minus reactants. Keep in mind the coefficients that go with each one when you do your calculation. So for this one, delta S for the reaction, we go products first. So it's equal to 8 times 213.6 plus 10 times 188.7. Those are all the products. Now minus the reactants, so minus 2 times 310.2 plus 13 times 205.0 joules per mole Kelvin. Remember, just like in the thermodynamics chapter last semester, we don't change any of the signs inside here. There's more than one way to work these problems. I think this is the easiest way, just products minus reactants, and you don't manually change any of the signs as you set this up. So we're ready to calculate our enthalpy, our entropy of reaction. Delta S for the reaction is equal to 8 times 213.6 plus 10 times 188.7. So far I have 3595.8 on my screen. Now I'm going to subtract 2 times 310.2 minus 13 times 205.0. I get plus 310.4. This is joules per mole Kelvin. So my answer for the reaction plus 310.4 joules per mole Kelvin, we should be able to tell whether this is an increase or decrease in entropy. Delta S is positive, so entropy is increased. During this reaction. The products have more disorder than the reactants. Now we'll work a couple more examples like this, just to drive home hopefully all the ideas that we're talking about. And then we'll get into deciding whether something is spontaneous or not based on H and S, both. Okay?